Hello everybody, welcome back. This is the 10.2 part 1 video, which will be going over understanding the relationship between exponential functions and logs, especially with graphing, and also to understand what the image looks like, what the graph looks like, and the features of a log function. And then in part 2, we will actually be converting between exponents and logs and evaluating log functions. And so first, again, just like the first video of this unit, I asked, what do I already know or remember about logarithmic functions? And so what I'd like you to do is please, again, pause the video, write down anything you remember from past courses, and I'll come back and show you what I wrote down. Please pause now. So here's a few things I wrote down. You could have had something different, and feel free to ask about it in class tomorrow. I wrote down that logs are related to exponents. This is a quick thought. I also wrote that I remembered that logarithms are inverses of an exponential function, which would make sense why we already went over exponential functions, so that we'd have a basis before going to logs. And again, feel free to ask on the next class period when we see you if what you wrote down is appropriate. So now let's get into graphs and the relationship between exponents and logs, and the fact that they are really inverses of each other. So the first thing we'd like to do is graph the function f of x equals 3 to the x, and then find and graph the inverse. So this is what we did the other day. So let's graph this with a table. X comma y, let's use -2, -1, 0, 1, 2, 3 to the negative second, 3 to the negative first, 3 to the 0th, 3 to the first, 3 to the second. Remember, 3 to the second is 9, so that means 3 to the negative second is not a negative number, but rather the reciprocal. 3 to the first is 3, so 3 to the negative first is 1/3, and anything to the 0th is 1. So if we plot all those points, -2, 1/9 is really close to the x-axis. -1, 1/3 is barely higher. 0, 1, 1, 3, and then 2, 9. Looks like this function, when the base is 3 instead of 2 in the last video, is rising much more rapidly, which does make sense because the base is bigger. Makes sense that the function would increase more quickly. And so here's a graph of our exponential function. And so if we recall from first semester, if we would like to find the inverse of this function, what we did was we replaced f of x with y equals 3 to the x. We then switched x and y, because the definition of an inverse is that x and y's trade places, and then you resolve for y. So if I do that, and I do x equals 3 to the y power, at this point I get a little stuck in terms of the solving. Because we haven't been reminded about how to use logarithms to solve, at this point we don't know how to continue the problem. But what we do know is, again, the definition of a inverse is switching x and y. And we have a table here. So what if, instead of solving this completely for y, I made another table, and this I'm going to write is really, this is what the log graph is going to look like, because logs and exponents are inverses. Every single y is going to become an x, and all the x's are going to become y's. So the points would become 1/9, -2, 1/3, -1, 1, 0, 3, 1, and 9, 2. And so if I plot all of those points on here in red, 1/9 is barely past 0, 0, -2 would be right there. 1/3, -1, 1, 0, 3, 1, and then 9, 2. My function would look, in my opinion, very much like an inverse. Here's why. If you're thinking about that an inverse, again, you just switch x and y, that means that these two graphs have to reflect around the line y equals x, because x equals y and y equals x. That means you can switch them interchangeably. And so your graphs are reflecting along that line y equals x. Other things to point out in terms of domain and range at this point. If you look at the blue graph, it's good to look at domain, range, and intercepts. notice that the y-intercept of the blue graph is 0, 1. So I'm going to write a note here. We're talking about the exponential graph versus the log graph. So the exponential graph, the y-intercept was 0, 1. If you look at the log graph, it does not have a y-intercept because it does not cross the y-axis, but it does have an x-intercept at 1, 0, which makes sense because the x's and the y's flipped. Pretty neat. If you look at the blue graph, we said in the video, the last couple videos, that it had an asymptote at y equals 0. So this time, if you think about them being inverses, the asymptote would be the line x equals 0, because this time the graph doesn't touch the y-axis, not the x. In terms of domain and range, the domain of the blue graph was negative infinity to positive infinity, which would make sense that the range of the red graph would be negative infinity to positive infinity. Because if I look at my red piece, it's going down forever and up forever. So the inverses, so the domain of the original is the same as the range of the inverse. Let's see if that's true for domain and range the other way. The range of the blue graph was 0 and above from the last video, so 0 to infinity, is the domain of the red graph, 0 to infinity. Well, if you're thinking about x values, you're going from the y-axis on, so yes it is, 0 to infinity. So just like first semester, everything flipped. The points flipped, the asymptotes flipped, the domains and ranges also flipped. Pretty neat, I have to say. So something that's going to help us graph a lot of log functions is to think of a generic log function, or a better word for that is a parent function. And so if you have a basic log graph, let me pick instead of b. Let's graph f of x equals log base 3 of x. And so logs, you'll learn soon, are exponents. And in the next video, everything I'm about to say will make more sense, and I'll come back to that. But I'd like for us to look at the red graph. If you have a generic log graph, the reason I picked log base 3 here was because I was given 3 to the x over here. Please note that this red graph went through the point 1, 0. So every generic parent function of a log graph is going to go through the point 1, 0. Always. If there's no movement, if it's just a basic function, it'll go through 1, 0. Another point it'll always go through is your base, comma, 1. So in this case, because my base is 3, it's also going through the point 3, comma, 1. So my next point would be right here. Another thing that's always true about the parent function of a logarithm graph is it's going to have a vertical asymptote. And so your graph, the basic one, is always going to look something like that. The reason that's helpful is that we can now view logarithms as the movement of a parent function, that we could translate or move up, down, left, right, shift it based on this idea. And again, in the next video, I'm going to come back to this and show you why the points 1, 0 and the base, comma, 1 are always on the graph, but just kind of hold on for me there. Here's the last example in this video. What if I wanted you to graph log of x plus 2 minus 3? Let me change this problem a little bit. Let's do f of x equals log base 5 of x plus 2 minus 3. So instead of having the base of 10, which you'll learn about later, let's do this problem instead. So what I would like to point out is that if, again, you have a parent function, a basic one like this, you can use the points 1, 0 and base, comma, 1. So think about what the x plus 2 and x minus 3 mean. This eventually means that I'm moving to the left 2 units, and this means that I'm moving down 3 units. But before any of that happens, I need to think about my parent function, which would be f of x equals log base 5 of x, the most basic one. And so if I have this parent function, I know from the previous problem that it's going to go through the point 1, 0 for sure, and it's going to go through the point b, comma, 1. In this case, b is 5, so it's going to go through the point 5, comma, 1. Now, if you think about translations, let's see what happens to these 2 points if I do these 2 things. If I move left 2, the 1 is going to become a -1. The 5 is going to become a 3. If I move down 3, the 0 is going to become a -3, and the 1 is going to become a -2. So that means that if I were to plot this new graph, I would plot these 2 points first. -1, -3 would be right here. 3, -2 would be here. And then I'd also have to think about the vertical asymptote. In the original parent function, the vertical asymptote, or the parent function, is on 0, 0. However, this graph shifted left 2, so this line is going to shift left 2 as well. So I hope it makes sense to you that the vertical asymptote would be moving from the y-axis over 2, which means that my graph would look something along the lines of this. And I know that's not perfect, but it gives you at least a good sketch, and it looks like the inverse of an exponential function. So to summarize here, whenever you're given a log function, I would think of the parent function first, write down the 2 coordinates that go with it, and then consider the transformations between the 2. And again, in the next video, I'm going to reiterate to you why these 2 points actually occur, because the definition of a log. All right, so I'll see you on part 2. Thank you.